Okay, hi. In this video, we're going to go over simple searching using C++ code or C code. We're going to be just looking at linear and binary search. So this should be a relatively short video. So we're going to look at sequential search. Our textbook calls it sequential search. It's also known as linear search. So if your list is unordered, I mean, there are other kinds of searches, but almost all of them require some sort of a data structure or ordering or something on the search. So if you just have like an unordered collection of items, you have to do linear search, or you have to do something to the data to put it into a data structure to do better. So, and this is this week we're going to start talking about an important topic. We're going to be looking at the performance characteristics of different algorithms. So you're going to learn about get a basic introduction to the topic known as analysis of algorithms in computer science. So this gives you kind of the tools to be able to compare two algorithms to see which one will do better or worse as the number of items that you need the algorithm to handle gets bigger. So we'll look at sequential search. And then we're going to look at binary search. So binary search is actually a much better performer, but it only works on if you first sort the list. So you actually have to get your data ordered, like alphabetically or numerically from smallest to largest value, and then you can do a binary search. But as we'll see, it performs a lot better than doing a linear search once you get your data in your data structure. So as usual, I will have this example code in here. This week, or this video I should say, I'm pretty much using the functions shown in our course textbook almost directly. So the sequential search function and the binary search function. So Let's look at, although I did make one little change, so I noticed, we've kind of been just always using lists of integers when we've been doing examples, so I wanted to do something a little bit different. So we'll change our binary and linear search to use lists of strings, or arrays of strings in our case in the C language, okay? So we're going to start off with a list of basically 20 random names, and they're not sorted, okay? And let's look at our sequential search and go back to the function and discuss it a bit. It should be up at the top of the file. So sequential search takes 3 parameters, like in our textbook, although in our case it takes a list of strings instead of an array of strings instead of an array of integers. So the idea is we want to search this array for a particular item. So the third parameter is the item that we want to search for, right? And the second parameter, so because C arrays don't have their length as part of the abstract data type, we have to pass around the length as well for functions that we want to write to use basic C arrays, right? And in this case, the function returns the index of the item in our array, okay? So if the item is found, it should return an index between 0 and list length minus 1, right? So again, if our list has 5 items in it, the list length will be 5, so the valid indexes should be 0 to 4. Or in our example here, our list has 20 items in it, the valid indexes are 0 to 19, okay? So if we find the item, it's going to return the value from 0 to 19. If we don't find the item, the textbook just returns -1. I don't like using magic numbers, so we should define a global constant. I'll just call it not found. Again, this is mostly here just to make our code more readable, right? So instead of returning -1, you have to wonder what that is. If you're just looking like at this screen of code here, we see that it's returning not found. Yeah, so should make it more readable. All right. So the thing about linear search, since the items have no order to them, you can't do anything better than to just look at every item until you find what you're searching for, okay? So you might as well write a loop where you start at location 0, so at index 0 in our array, and we say, is the item at index 0 what we're searching for? Nope. Okay, go to the next location. Is the item at index 1 that we're searching for? Nope. Just keep doing that. If we find it, we're done. Boom, we return the location. That indicates a successful search, and it shows what index, what location in the array that the item is. Here, I did change the code a little bit from the textbook. So here, if we get through this loop, that means that we never returned. So we never found the item and returned it, and we end up just hitting this then and returning our flag, this not found flag. Okay. I'm going to uncomment this just as a little bit of kind of a logging message. So we'll be able to see every iteration through our while loop here. We'll print out a little message here of what iteration that we're in, okay? All right, so let's build that and run. And let me go down and let's step through all these here. So kind of as we've done in previous videos, I've got basically kind of tests of, first of all, test of our sequential search function. Let's go ahead and run it. So first of all, we'll search for the item Logan, so the string Logan in here. This should be a successful search because it's right here somewhere around the 10th or 11th item. So I'll step over here, step over. So as soon as we do our search, we should get those log messages, and then it should be a successful search, so it should return the location that it finds. So we actually had to go 8 iterations. So this Logan must be at index 7 here, the 8th item in the list here. So if we step over, it's at index 8. Okay, so. There we go. All right, so keep that in mind. So to begin the discussion about the performance of the linear search, right? So, if we got lucky, if we were searching for Liam, we would just have to go one time through the loop, right? So it would turn right away with just one comparison. So checking if the search item was equal to the item at index 0, Liam, right? So we could get lucky and just be searching for the first item, return immediately, but we can be unlucky, want to search for Abigail. It happens to be the last item. So in that case, we'd have to do 20 comparisons, 20 iterations through the loop to find it, right? So you can prove this in statistics. If you take the statistics class, you can kind of see that. So given that you were equally likely to find an item, we would expect on average that we have to go through half of the items before we find it. Sometimes we get lucky, have to do fewer than half. Sometimes we're unlucky, we have to go off to the end or nearly to the end, right? But on average, they'll be in over 2. So on the average, it would take us 10 loops or 10 key comparisons to do this linear search for this list length of size 20, okay? And in the analysis of algorithms, we usually refer to the number of items that we have to be processing with our algorithm just as n. So in this case, our n, our size that our algorithm is dealing with is 20. N is 20, okay? Right. Although there's one, our textbook doesn't mention this. There is one important caveat for this. So this assumes that all or pretty much all of our searches are successful searches. So if you're always searching for an item that's in your list, your performance is going to be n over 20. So on average, you'll have to search about half the list. Okay. Now, so it's different if you're performing searches where there's a big chance that the item won't be found. Okay, so if it's not found, you have to search through the whole. You have to do 20 iterations through the loop, right? So you have to go through all the way through the list to determine, nope, the item isn't there. Okay, so for example, if 90% of your searches are unsuccessful, that means that 90% of the time you have to do a full n iterations or a full n key comparisons. Okay, so that changes your average quite a bit. So in that case, for 90% unsuccessful, you're pretty close to needing n iterations on average most of the time, just a little bit less than n, 20 in this case. All right. So yeah, that's the basics really of performance. That's all there is to the performance of the linear search. So let's just look at some other searches. Logan is we already did Logan. So Liam is the first one. So an example of getting lucky. So this should return index 0. So yeah, search for Liam was at index 0. Abigail was our last one. So again, this is kind of, I'm testing the edge cases here, so these are meant to be unit tests again. So make certain it can find the first item in the list and the last item in the list. So notice for Abigail, again we had to go through the loop 19 times to get all the way till before we found Abigail. We were actually in the 20th iteration of the loop. I should have put that log message at the top of the loop instead of the bottom. So we hit this log message 19 times, and then on the 20th time we found it and returned. But we had actually done 20 key comparisons. That was my mistake. I should have put that at the top here to emphasize that the exact number of key comparisons that we're making. So, all right. So that was Abigail. Lucas isn't in our list, so this is an example of an unsuccessful search. So we should have to go through all 20, and then we'll be unsuccessful and return our little flag, the -1, which indicates not found, right? So yeah, here we just check and then show it. All right. So that was the basics of linear search. So now let's look at binary search. So you can do much better, but again you can search much faster. If I have billions of items that I need to search, linear search isn't going to cut it. It's going to take a long time to search through billions and billions of items. You can be guaranteed that Amazon, when you do a search for something, is not doing a linear search. You'd be sitting there for years before you got your results back. Okay, so the simplest thing you can do is order your items from smallest to largest, or in this case, we're going to order the items alphabetically. The names here, right? We'll talk about sorting in the next video, so go to that. So just know that we can call an algorithm to sort our array. So we pass in the array and the size of it, and after returning from it, the array should be sorted. So let's just show that. So after that, here's our array: Abigail, Amelia, Ava, Benjamin. So A's through Z's, right? So we successfully sorted. So now that we're sorted, we can do our binary search. So let's look at the binary search. So again, this is pretty much directly the algorithm from our textbook. If you're in my class, our Malik textbook. So we take the same 3 parameters for this binary search. So we take a string of values, an array, a list of strings. Or an array of strings that we want to search. We take the item that we want to search, another string, the item we're looking for, and then the size of our list. And again, we're returning the integer. So we return a value from 0 to 19 for this list of 20 values. If we find it successfully, and we return not found if we don't find the item. So the strategy for a binary search is, so since the items are ordered, we can do this. This is basically what we do. So we first look at the item in the middle of the list. So initially we're looking at the whole list. So when we first start off, we set first and last, first to be the first index, index 0, and last to be the last index that actually holds an item. So for our list, it'll be 20 minus 1, or 19. So that means that we're looking at the whole list initially, and we want to find the item in the middle, okay? So we calculate the midpoint. So initially, that's going to be 19 plus 0 divided by 2. We do integer division here. So 19 divided by 2 is, what, 9.5? In integer division, we'll just chop off any decimal. So we'll get a midpoint of 9. Doesn't have to be exactly in the middle. It'll still work. So the idea then is we look at the item in the middle. Right now, if we found it, we could get lucky. So it could happen that we're actually searching for the 9th item, the item at index 9. So we just return. Actually, in this case, I set a flag to be true. This is actually the same thing our textbook does for this algorithm. So we set a flag to be true, which will cause the loop to exit. And then if we find it, we return what the current value of midpoint is, which should be the item. The index where we just found our item, right? But usually we won't find the item. But since the list is sorted, the item at this midpoint in comparison to the item we're searching for tells us something, okay? So if we look, and if the item at the midpoint, so this is going to be a string, if that's greater than the search item, that means that our search item must be alphabetically before that item. So if you think of this list as ordered from left to right, that means it must be in a smaller index, okay? So that means we can eliminate all the indexes from the midpoint to the last, and we want to concentrate only on the items from 0 up to the midpoint. Okay, so the first time through the loop, we're basically eliminating half of the list, and then we're going to look again, do the same thing again, but only looking at the items from 0 up to that midpoint, so 0 to 9 in the example I've been doing so far. Right, but the other thing could occur as well. So it could be that the string at the midpoint was less than the search item. So if it's alphabetically less, so if we were searching for William, and the item at the midpoint was Liam, that must mean that it was less. So it must be to the right. Okay, so that means that instead we want to search from the midpoint up to the end. Instead, we want to search that half of the list, okay? So that's a bit, and so notice, this is much more powerful than our linear search, because every time we eliminate half of our choices. So the first time, just going by whole numbers, if we have 20 items in our list, if we don't find it the first time, then we reduce our list from 20 to 10. And then the second time through the loop, we reduce from 10 to 5. And then the third time through the loop, we reduce from 5 to our worst case down to 3 items. And then from 3, our worst case is down to 2 items, and then from 2 to 1. And then from 1, we're guaranteed we either found it or we know that it's not in our list, okay? So jumping ahead here, that's a logarithm, basically a log base 2, right? So if I have a list of 1,024 items, it's going to take me log 2 of 1,024, which is 10 iterations, 10 halvings before I get down to there's only one item left, because I go from 1,024 to eliminating it down to only 512 items, from 512 to 256, from 256 to 128, and there's only 10 halvings before you get down to 1, right? So the log base 2 tells you for some size of n, what's the maximum number of iterations I'll have to go through. I could go through less. I might find it on the very first, right in the middle, or the second or third time where I have the list. But at most, I'll have to go log base 2 of whatever the size of my list is. All right. So hopefully, if you don't understand that, make certain you do. Right. So that's an important thing to understand about understanding how the analysis of algorithms works. So understanding the performance and being able to compare the performance of algorithms. So, all right. So yeah, that's the basics of binary search. So let's look at it in action. So, again, for binary search, the version I gave you, we have a little log message. This was the main reason why I put back in that little flag, so we could have the log message. There is two within the loop. There's a log message. So every iteration through the loop, we print out the iteration number, and we print out what the current first and midpoint are, first and last, and the midpoint are. And then at the end, we print out some information. All right. So let's just look at this in action here. So first, let's search for Logan. So Logan is we need to look at our sorted list here. So Logan comes, again, approximately in the middle, a little bit past the midpoint. So, eyeballing that looks like index 11 or 12 or something like that. So we'll step over. So, I just told you that we should only need a maximum of 5 iterations for 20 items. Log 2 of 20 is 4 point something, right? You have to kind of round it up to get what the maximum is. because 2 to the 4 is 16 and 2 to the 5 is 32. So it could take a little bit more than 4 iterations. It did take us 4 iterations. We found it at index 12 here, right? I should have searched for the item exactly in the middle to show that it could take 1 iteration or 2 iterations. But anyway, I'm sure you believe me. William was the last item. So here's the worst case. Actually, the worst case is again an unsuccessful search. But yeah, if you search for an item at the beginning or the end, that should also take you the maximum number of iterations to determine that the item is in there. So let's step over that. There's our search. So yeah, so we see that to get William at index 19, it takes us 5 times through the loop. So again, here, you know, the little log messages are to try to help you understand what's happening. So initially, first and last are 19. We set the midpoint at 9. So remember, we're looking for the item at index 19. So since we didn't find it, then every time we're going to set mid to be the midpoint. We're going to set first to be the midpoint. So the next time, the midpoint plus 1. So the next time we've eliminated the items from index 0 to 9, and we're searching from 10 to 19. We don't find it at 14, and it's still greater than 14. So now we're going to search from 15 to 19, and the item in the middle of that is 17, and it's not at 17, and we determine it's greater than 17. So we search from 18 to 19, and then finally your last time through the loop, the first and last will be equal. And that's the stopping condition to tell that you've exhaustively searched the list and know that either the item is in it or the search is unsuccessful. So when first is equal to last, you have to do one final search, and at that point first is going to be less than last, and then when they cross each other, you know that you've searched everything in this typical iterative way of defining the binary search here. All right. So that was searching for the last item. So here's again similar thing, but we'll search for the first item, the item at the very beginning of the list. So again, we'll need we only needed 4 iterations there before we determined that it wasn't in there. So, and then another more. Oh, this is an unsuccessful search. So again, an unsuccessful search should always take 5 iterations to eliminate, you know, to be certain that it's not in there when we have 20 items in our list that we're searching for. So. Okay, so that's the basics of the linear and binary search. So so as I said, you know, this tells us that the number of times through the loop, and since we're only doing one comparison each time for the sequential search, we're going to have to do n divided by 2 comparisons on average. That's our performance for the sequential search, but the binary search, you know, at worst, we're going to have to do log 2 of n. So if n is the size of our list, we'll at most have to do log 2 comparisons. This is kind of an upper bound. But each time we're doing 2 comparisons. The reason for that is that, again, if you look closely at the linear search, we check if it's equal, and then we check if it's greater than. So those are the 2 comparisons. So if you look at the textbook, it says that the performance is 2 times the log of n, which is true, right? So that's actually the number of key comparisons we'll have. We only have to do 1 comparison every time that we iterate on the sequential search, but 2 for these. Okay. So one final thing then. This is kind of a preview for next week when we get deeper into talking about analysis of algorithms. So let's look at the performance, comparing the performance of n over 2, which is the sequential search, to 2 times log 2 of n, right? So on the x-axis is n, the number of items in the array that we want to search. This is a log-log scale, so well, I'll get to that in a second here, but yeah. So here, this is what if we have 10 items in the list. This is if we have 100 items in the list we want to search, 1,000 items, 10,000 items, and 100,000 items. So you should see that even with 100,000 items, it only takes the binary search a little over 10, so that's about, what, 50 comparisons to be guaranteed, 25 iterations through the loop, and 2 times that to guarantee, to find the item, right? But for the linear search, it's going to take half of 10,000 of 100,000, 10 to the 5 100,000. So that's 50,000. So this grows much quicker than that. So there's no comparison. I mean, binary search is going to be almost immediate. So even if we have a billion, 10 to the 9, it's still only going to take less than around 100 comparisons to search a billion. But it's going to take half a billion, so half a billion searches might take you hours, depending on how fast your computer is. But we're still only taking about 100 comparisons to do the binary search. So that's why being able to compare the performance characteristic is important. So it's impossible to search linearly through a billion items. You'll be waiting for a long time, even on a really fast computer. But binary search is going to return almost immediately, right? And one final quick thing. So the performance of the bubble sort, or all of our sorting algorithms that we look at, is about n squared. So n squared, if you compare a logarithmic performance to n, which is a linear performance, and then if you compare linear performance to n squared performance, that's even another jump. And again, the log scale here doesn't do it justice, right? So again, for 100,000 items, the n over 2 is going to take about 50,000 comparisons. So 100,000 divided by 2. But an n squared algorithm is going to be 10 to the 10. That's 10 to the 9 is billion, so that's 10 billion, right? So, that is going to take, even for just 100,000 items, that's going to take hours for an n squared algorithm. All right, so I think we covered everything. That's the basics. Like I said, this is just a little bit of a setup for talking about the analysis of algorithms. But here we only looked at search. So in the next video, we'll look at sorting algorithms. We'll look at a couple of different sorting algorithms. But that's it for this video. So I'll leave it there, and I will see you in the next one.